extreme high energy end of the electromagnetic spectrum. How high in energy? Well, the light that we see with our own eyes corresponds to a few electron volts, which is the unit we use for describing energy. The photons that GLAST will study in gamma rays are literally millions to hundreds of billions of times as energetic. So you can see we're really probing at a very different energy scale. The other thing that's important is that those energies are so high that the famous E equals mc squared equation from Einstein turns out to be very important. The energy is so large that it's possible to use it to make bits of matter and antimatter, as Kevin showed. And a gamma ray can convert into an electron and its antimatter partner, a positron, in the presence of material. And that is a key way in which we use to detect the gamma rays, as we'll see in a couple of minutes. So why do we have to go into space? Well, the gamma rays have no trouble getting to us across the visible universe, 10 billion light years, but in fact they just go splat. They just splatter on the upper atmosphere, and the reason is all that kinetic energy available in the gamma rays is converted into lots and lots of particles, and we lose the information about the initial gamma ray. If the initial gamma ray energy is high enough information about that splatter actually reaches the ground, and we can do gamma ray astrophysics from the ground. But in the key energy range we're going to study with GLAST, you just have to go into space to be able to intercept and measure the properties of those gamma rays and send the information down to the ground. Now, since gamma rays are at the extreme high energy end of the electromagnetic spectrum, it's not a surprise that they tell us about the most extreme environments throughout the universe. Places where gravitational fields are extremely strong, magnetic fields and electric fields are absolutely enormous. So large that you couldn't possibly make those conditions on the Earth. One of the important reasons we're here today is because of one of NASA's great observatories, the Compton Gamma Ray Observatory, which operated from 1991 to 2000. And the high energy instrument on that observatory, called EGRET, and its predecessors, showed us the tip of the iceberg. So here's a quick tour of what we know about the gamma ray sky, along with some key questions that we think GLAST is going to address. So next graphic, please. If you want to look at the whole sky, but represented on a television picture, you have to find a way to project it. If you think about a beach ball and looking inside of a big sphere, you need to slit it and then unroll it, flatten it, and that's what this image that you're seeing now, what has been done. So imagine the left and the right parts of the image just rolled up together and touching each other, and that's what you see here. This is handed down to us from the high energy instrument EGRET on the Compton Gamma Ray Observatory, and there are some amazing features that I'd like to point out. If we can go to the next graphic, please. That big bright glow that you're seeing along the middle of the image is actually our own Milky Way galaxy, and it glows like gangbusters in gamma rays. And the principal reason for that, we think, is that there are very high energy cosmic rays that are made and propagating throughout the galaxy, and they run into interstellar material, gas, and the kinetic energy of those cosmic ray particles is converted into other particles, including gamma rays. So gamma rays reveal to us the distribution of high energy particles throughout our own galaxy and the distribution of material throughout the whole galaxy. And that alone is incredibly interesting, fascinating, and important, and gives you a sense of how different the gamma ray sky looks. I'll give you another example. In the gamma ray band, in fact, the moon and the Earth are actually brighter than the sun. So that tells you again how unusual the gamma ray sky is and how different it looks to us in gamma rays from our own natural eyesight. There are a lot of questions about this galactic emission of gamma rays. For example, many people suspect that there are clues to the nature of dark matter, a form of matter that's completely unknown to us at this point, except that we know that it composes the vast majority of matter in the universe, and we'd love to understand much more about it. There are many experiments around the world looking to study the properties of dark matter. GLAST will contribute uniquely to those searches. And there may be important science lurking in that signal. Next graphic, please. Throughout the galaxy, in fact throughout all galaxies, are very rapidly spinning neutron stars. A neutron star is the collapsed core of a very massive star. It's so dense that 1 billion tons of neutron star material would fit into a size of about a tablespoon. So that just tells you how incredibly different an environment we're talking about. And the magnetic fields are enormous. These things are spinning around sometimes 1,000 times a second, making huge beams of very strong magnetic fields, which when rotating make strong electric fields, which accelerate particles and generate gamma rays. And we would like to know what is the geometry of those systems, where are the gamma rays emitted, how do they work. GLAST will be very important for that, combined with radio observations. Next. We now think that at the core of most, if not all, galaxies is a supermassive black hole, millions to billions of times the mass of our own sun. You might be thinking, well, if the sky is black and a black hole is black, how could you possibly see anything having to do with black holes? A little bit like the famous paintings of Ad Reinhardt. Well, in fact, a black hole has a huge impact on its environment, and the environment has a huge impact on a black hole. And in the centers of galaxies, where there are these immense black holes and a huge amount of material for them to eat, as the material falls in, enormous amounts of power are liberated. In fact, we see coming out of these galaxies very collimated jets of very high energy particles that are literally blown clean out of the galaxy. And we'd like to know how that happens. How is this possible? When those jets happen to be pointed roughly toward our direction, we see the galaxy and the core of the galaxy as incredibly bright in gamma rays. So much power is emitted just in gamma rays that it's the equivalent to all the suns of an entire galaxy shining over all wavelengths or more. And their sources are variable on various timescales from minutes to years. What is that variability telling us? What kinds of clues is it telling us about what composes the jet? And how is this even possible? What's the underlying energetics? GLAST is going to be key for studying this because, as Kevin mentioned, we're going to be able to see the entire sky every 3 hours, be able to probe that variability over very vastly different timescales. And that's just a bonanza to scientists who are interested in studying these systems. I should add that combining GLAST data with other data from other facilities, such as radio facilities, optical facilities, and X-ray facilities, is absolutely key to studying these objects. We'll all work together. And that's one of the delightful things about working on GLAST, is the great connections that GLAST makes with lots of other science investigations. If I could have the next graphic, please. About once a day, somewhere in the visible universe, there's an enormous explosion, and it's a gamma ray burst. So much energy is liberated that in about a second, enough energy comes out that it's comparable to the amount of energy that will come from our own sun over its multi-billion-year lifetime. So just in a second, such amounts of energy are released. We'd obviously like to understand these things better. The key thing that GLAST is going to provide is to tell us what the energy budget is for these incredible engines. We'd like to know how they work. We'd like to know how high in energy they can go. And GLAST is going to open up a key new energy band for their study. Next graphic. Finally, EGRET gave us not only all this great information, but a big puzzle. Of the 271 point sources that EGRET was able to see, the vast majority of them, about 172, are unidentified. Not unidentified in the sense of a UFO where you see something and you don't have a clue what it is, but in fact the error circle for EGRET was sufficiently big that there were various counterparts in that circle, and we just don't know what it is. GLAST is really going to